Hi, my name is Savannah Harris and this is my Lab 2 video presentation. Here you can see my tracker video. For this video I dropped a foam stress ball because I knew it would exhibit signs of drag better than a heavier object, for instance, let's say a baseball or a textbook or a rock like they said on WebSign. Here is my y versus t graph. As you can see, the slope is steadily getting steeper because you don't have constant velocity here. In fact, the ball is speeding up in the negative y direction. Here's the code that I edited to fit my model. This model does not include drag, and the first variable I inputted was the mass of the foam ball, which was 25 grams, so here it is 0.025 kilograms. The time step was left at 0.001, gravity was given at 9.8. The next thing I had to do was to find the weight force. Here you can see that weight force is the mass of the ball times gravity times j hat. Next, I set the net force equal to weight force since we are only concerned with weight force in this particular model. So this is what it looks like when the code is run. As you can see, there's a y versus t graph as well as a visual representation of what it should look like. The next thing I did was compare my tracker data to the data from the model. Here you can see each of those data sets represented. As you can see, the model expects my ball to drop farther than the ball actually does in real life, and this difference can be explained by drag. So here is my code for the model that includes drag. For this I created a variable fd, which stands for drag force. I set it equal to b, which is a constant I found through trial and error runs while attempting to get the final y position of my model and my real drop to be the same, times the magnitude of the ball's velocity squared times j hat. This is what it looks like when you run the code. It's almost identical to the previous model, but you can see there are differences here in this graph that shows the position versus time. As you can see, when drag is not accounted for on the blue line, the object is expected to fall a little bit faster. This is because of the force of air pushing up on that object is not taken into consideration. When an object falls, there is resistance from the air because in order for the object to fall, it has to push air out of its way, which creates drag and slows the object slightly. The red triangle is the observed position of the ball as it fell. You can see that the ball falls slower than the model with no drag predicted. The yellow line is the model that contained drag. As you can see, the ball ends in the same final position as the yellow line does. This is a result of purposefully selecting a b or drag constant that causes these two to have the same final position. As you can see, the faster the object falls, the more effect drag will have. This is why the yellow line gets farther away from the dragless blue line as time goes on. This is indicative of what's called terminal velocity. At terminal velocity, an object ceases to accelerate even when the force of gravity is acting on it because the drag of the air is equal to the force exerted on the object by gravity. So for instance, think of a skydiver. At a certain point, even when he is still in free fall, the skydiver will no longer accelerate because the drag force cancels out the gravitational force, which causes the net force to be zero and therefore no acceleration takes place. So this lab asked us to investigate the question, what if an object was initially thrown downward? Would the terminal velocity change? And the answer to this is no. While your initial speed would be greater than zero, you're not adding any additional forces to the object while it's in the air. Only gravity and drag are acting on it as it falls. And that's why those are the only two accounted for in the code. I actually entered this scenario into the code and ran it. The position versus time graph initially had a decreasing slope, a slope that was getting steeper, but after a while the line straightened out to have a constant slope, and therefore a constant velocity, which is indicative of terminal velocity. So after a certain period of time, the object stopped accelerating, its velocity became constant, and therefore it reached terminal velocity. The terminal velocity is also the same speed. The terminal velocity is the same speed that the same object dropped from rest would reach at terminal velocity. The beginning velocity of an object does not interfere with its terminal velocity. Before I finish, I want to quickly recap some of the possible errors that would have caused my yellow line to be a little bit off from the red triangles. Some of the things that could have affected this would have been the way I dropped the foam ball. Maybe if I had accidentally dropped it and given it a tiny upward velocity by moving my hand up and away as I dropped it. This could have changed the initial velocity and therefore changing the rest of the graph. Another reason is that it was filmed from an angle, and that's why you see that the line of the wall is actually slanted. So that could have changed it as well.